Welcome to another module in this massive open online course on estimation for wireless communication systems. So, in this module we will start looking at another paradigm or a new technique of estimation which is termed as sequential estimation. So, let us start looking at sequential estimation. Basically, sequential estimation is about how to continuously keep estimating. As the name implies, the estimation is being carried out sequentially, that is, which means that the estimate is being continuously updated as and when the observations are arriving, all right. So, basically this means that your estimate, you do not have a fixed estimate, but the estimate is being updated, and that is the key word, updation or updating the estimate. Estimate is being updated continuously with the new observations, yeah. With the new observations, and this is very relevant in the context of wireless communications, because all the time there are new observations, that is new pilot symbols being transmitted and new received output symbols, that is new output symbols being received. So, with every new output symbol one can basically update the estimate of the channel coefficient, all right. So, this paradigm of basically sequential estimation, of continuously updating the estimate, is very relevant for wireless communication. So, basically this is very relevant for wireless communication. This is very relevant for a wireless communication setup, since the pilot symbols are arriving or the pilot outputs are arriving continuously, or pilot outputs are available, let us say they are available sequentially, right, they are available sequentially, and that is the key term here, that is they are not available all at the same time, but they are available sequentially, in the sense that there is a pilot symbol transmitted, there is a pilot output that is observed, based on which you compute the estimate. At the next instant you have another pilot symbol that is transmitted, and you have a corresponding pilot output. So, one need not compute a fresh estimate, or one need not recompute the entire estimate, rather one can simply update the previous estimate, and that is really the keyword here. That is, instead of recomputing the estimate at every time instant, one can simply update the estimate from the previous time instant. So, let us summarize that. Instead of recomputing, so what is sequential estimation about? Instead of recomputing the estimate, simply update the estimate from the previous time instant. Simply update the estimate, and that is really the key, that is to update the estimate. How do you update the estimate from the previous time instant? And to understand this, let us go back to our example. Let us look at this to illustrate this with the help of an example, all right, or a certain estimation scenario that we have already considered. Let us go back to our channel estimation, that is where we are estimating the fading wireless channel coefficient. So, let us illustrate the sequential estimation for the wireless channel, sequential or the wireless fading channel. So, let us call this as sequential wireless sequential wireless channel estimation. And remember, in wireless channel estimation, something that we already described, we have the transmitter, this is your transmitter, you have your receiver, this is your receiver. Let us consider the simple scenario where we have a single transmit antenna, where we have a single receive antenna. So, these are basically the antennas, and the channel between them, the transmitter and receiver, is represented by the fading coefficient. This H, if you might remember from the previous modules, this is your fading coefficient or the fading channel coefficient. So, H is the fading channel coefficient, H is basically your H is the fading channel coefficient, and estimation of H, estimation of this fading channel coefficient H, this is termed as channel estimation, that is a wireless channel estimation. So, estimation of H is termed as wireless estimation of H is termed as wireless channel estimation. We transmit towards this end, we transmit the pilot symbol xk from this and receive the corresponding pilot output symbol yk, okay, and the system model for this can be expressed as the system model for this. This is something that we already seen, which is yk equals H, that is your fading channel coefficient H, times xk plus Vk, and what are the different quantities here? Yk is the received output symbol at time instant k, this is the received output symbol at time k, H is the fading coefficient, xk is the transmitted pilot symbol at time instant k, and Vk, as we are already familiar, this is the IID Gaussian noise mean 0. So, this is the noise sample, and we are assuming IID Gaussian noise with mean equal to 0 and variance equal to sigma square. Okay. So, we have the same familiar model, that is yk equals H times xk plus Vk, yk is the output symbol, H is the channel coefficient, xk is the kth transmitted pilot symbol, and Vk is the noise sample, alright. And now let us consider the transmission of n pilot symbols, capital N pilot symbols similar to before, and then we will adapt this, or we will modify this model for the sequential estimation scenario. Okay. So, similar to before, this part is similar to before. Consider the transmission of n pilot symbols. Consider the transmission of capital N pilot symbols, and therefore, we can write the received symbols y1 equals h times x1 plus v1, y2 h times x2 plus v2, yn equals h times xn plus vn. All right, these are the n received outputs. These are the n received pilot outputs. x1, x2, xn are the transmitted, x1, x2, xn are the n transmitted pilot symbols. What are these? These are your n these are the n transmitted pilot symbols. Now, we can represent this by a vector. I can write this as your vector y bar, y1, y2, yn is your vector y bar, this is the n dimensional vector, x1, x2, xn is the pilot vector, this is x bar which is your pilot vector plus v1, v2, vn which is the noise vector v bar. So, I can now write this as, and this is also something we have seen before succinctly using vector notation, or let me just write x bar times h plus v bar. So, this y bar is the n cross 1 output vector, x bar, what is this? This is your n cross 1 pilot vector, h is of course the channel coefficient, v bar is the n cross 1 noise vector, and this is also something that we have already seen before, that is you have y bar equals x bar times h, the channel coefficient h plus v bar, where x bar is the n dimensional pilot vector. Okay. And then we computed the maximum likelihood estimate. Okay. The maximum likelihood estimate which maximizes the likelihood, that is estimate which maximizes the likelihood, is h hat equals x bar transpose y bar divided by x bar transpose x bar equal to x bar transpose y bar divided by norm x bar square, which is equal to, I can write it now in the form of the summation, we have also seen this before, k equals 1 to n x k y of k divided by summation k equal to 1 to n x k or x square k. Okay. Norm x bar square, the norm of the vector square is basically summation k equal to 1 to n x k square. Okay. Now, we are going to make a small modification, not exactly a modification, a simple change in the notation. Instead of calling this the estimate h hat, we will be calling this the estimate h hat of n, that is the estimate at time instant capital N based on the pilot symbols x1, x2 up to xn. Alright. So, in the paradigm of sequential estimation, because we are computing not one estimate, but we are updating the estimate at every time instant, the time instant, so the estimate is also now characterized by time instant. So, h hat becomes h hat of n, which denotes this is the estimate at time instant n. This is the estimate at time instant n, okay, and this is computed based on pilot symbols x1, x2 up to xn transmitted up to time instant n. Okay, so, what we are saying is this estimation now in the sequential estimation scenario, this is a continuous process, right. So, at each time instant we are going to compute, we are going to update the estimate at each corresponding to each time instant. Basically, as the pilot symbols are arriving, as the pilot outputs are arriving, we are going to continuously keep updating our estimates. Hence, naturally there is not one estimate, but there is an estimate for each time instant, and this estimate h hat at time instant capital N, we are denoting it by h hat of n, which is basically computed from the transmitted pilot symbols small x1, small x2 up to small xn, and the corresponding of course received pilot outputs, observations, which are basically the small y1, small y2, small yn. So, let me also mention that corresponding pilot symbols, and naturally it goes without saying also the corresponding observations, because the observations are also have to be used to compute the estimate. Okay. So, also now the variance of the estimate at time instant n, remember we have also calculated the variance this is equal to, let us denote this by P of n, this is the variance at time instant n, let us denote this by the quantity P of n, and we know that this variance at time instant n, this is P of n, this is equal to sigma square divided by norm x bar square, which is basically equal to sigma square divided by summation k equal to 1 to n x square of k. So, basically your P of n, the variance at time instant n equals sigma square divided by summation k equal to 1 to n x square of k, and what is this? This is the variance of the estimate at time instant n. Variance of estimate at time instant n. So, we have two things, one is we have h hat of n, which is the estimate computed at time instant n, and then we have P of n, which is basically the variance of the estimate at time instant n. Now, based on these two, we will update the estimate at time instant n plus 1, that is at the next time instant. So, for the next time instant, now consider the transmission of pilot symbol x plus 1. For the next time instant, transmission, consider the transmission of pilot symbol x n plus 1, that is pilot symbol at time instant n plus 1, and corresponding received symbol observation be y n plus 1. So, let corresponding observation let the corresponding observation be y n plus 1, which basically implies that your y n plus 1 equals, what does this mean? Y n plus 1 equals h times x n plus 1 plus v n plus 1. So, this is the model at time n plus 1. Your model for the next time instant n plus 1. Okay. So, we have y n plus 1, which is the pilot symbol, received output symbol at time instant capital N plus 1 corresponding to the pilot symbol x n plus 1 transmitted at time instant n plus 1 by the transmitter. Alright. So, now we have to update this. So, now we have a new observation y n plus 1, and therefore, based on this observation we have to update the estimate h hat of n to h hat of n plus 1 at time instant n plus 1. So, based on this new observation, so now the task in sequential estimation is, now we need to update h hat of n to h hat of n plus 1 based on x n plus 1 and y n plus 1. Okay. And now you can see, basically it is very simple to see that the pilot estimate at time instant n plus 1, let us first write it this way, h hat of n plus 1 equals summation k equal to 1 to n x k plus 1. It is very similar to what we have written at time instant k, summation k equal to 1 to n, instead of, I am sorry, k equal to 1 to n x k times y k, k equal to 1 to n plus 1, k equal to 1 to n plus 1, x square of k. And in fact, this is something that we have, it is very similar to what we have written here. For instance, at time instant n, we have summation of k equal to 1 to n x k y k divided by summation k equal to 1 to n x square of k. Now, instead of n, basically all we are doing at time instant n plus 1 is we are changing the index, changing the limit on the summation to n plus 1, that is we are including now n plus 1 transmitted pilot symbols and n plus 1 received output symbols. However, this is not the right approach to that, because we are recomputing again the entire estimate. Remember, the whole idea was to use h hat of n, that is the estimate at time instant n, and p of n, the variance of the estimate at time instant of n, rather than recomputing the entire estimate at time instant n plus 1. And that is what we are going to slowly do. That is what we want to do, is basically we want to we do not want to recompute this estimate at time instant n plus 1, rather we want to intelligently use the already existing, the already computed estimate, that is h hat of n at time instant n, and that is what we would like to do. What we would like to do is, rather than recompute the entire estimate, update, we would like to update estimate based on your h hat of n and p of n. H hat of n is the estimate at time instant n, this is your estimate at time instant n, and p of n is your variance of estimate P of n is the variance of the estimate at time instant n. So, what we are doing is basically we have computed the straightforward estimate, which is basically recomputing the entire estimate at time instant n plus 1, but that is not what we want to do. We want to in fact intelligently update the previous estimate, that is h hat at time instant and h hat of n at time instant n, and using the variance p of n at time instant n. Alright. So, in this module what we have done is we have introduced this new concept or this new framework of sequential estimation, where we are not computing a single estimate, but rather we are updating the estimate at every time instant. We are looking at it, we have introduced the model for this in the context of wireless fading channel estimation, where we have considered the time instant h hat of n or the fading channel coefficient h at time instant n, and the variance P of n at time instant n, and subsequently we have also considered basically the transmission of a pilot symbol x of n plus 1 and the corresponding received observation or measurement y of n plus 1, and using this we would like to now basically compute the sequential estimate h hat n plus 1 at time instant n plus 1. Alright. This we will do in the subsequent modules. Thank you very much.